Good, cool. All right, so with that, we can kind of launch into the quick tour of SST elements. So as I said, kind of the earlier part mainly focused on the SST core and framework, sort of what SST is. And the key thing about SST is that it's not a simulator, it's this toolbox or this toolkit or framework of a variety of different components. And the actual, useful part, the architectural experimentation part, lives in those components. SST's core, though, provides the glue, which kind of brings them all together and provides all sorts of useful services. So a big goal in creating SST, of course, was this modularity that we realized the simulation problem is far, far larger than any one group can really accomplish. So SST's core is there to provide leverage and provide a mechanism for people to not have to reinvent the wheel. Anyone could create their own parallel discrete event framework, but it does take a lot of work, and as architects, we want to do the architecture work, not spend the man hours on creating the infrastructure and getting it ported and getting it regression tested and so forth. So the big goal of SST's core was to allow that reusability, create a framework for that modularity and composability, allow us to mix and match these different components, but then the components themselves hopefully will end up being kind of the real star of the show, and that's where really more effort actually goes, and what actually allows us to create the architectural experiments which are ultimately the driver for all of this activity. So the way SST is organized is the core and the elements. The core, of course, provides all those services and the parallel discrete event framework. The element libraries provide the actual, useful simulation components. So libraries library will contain a set of related components, subcomponents, and modules. SST ships with a number of built-in libraries for processors, memories, and network. We'll be talking about some of those. There's also, we do a lot of internal regression testing to ensure a lot of those component libraries work together. And also, we provide some compatibility for many external libraries, things like DRAM to Gem5, or later this afternoon we'll be hearing about a high bandwidth memory simulator. The website, ssdsimulator.org, has some detail on some of these libraries. There's also SST info, which gives kind of parameters and port names and things of that sort, and some of these have been detailed in different publications. So some of the libraries which will be shipping in SST 6.0 and which should be in the release candidate on the virtual machine which was distributed. For processors, we have 3 different models, one of which is Aerial, which uses Intel's pin tool to take instruction traces, particularly memory traces from a running application using dynamic instrumentation. Prospero, which can take a trace of memory accesses, and Miranda, which is a pattern-based processor model. So by pattern-based, we mean sort of construct a little state machine which generates a memory access pattern, which we can then feed into our memory hierarchy and network on chip models. For memory, probably the central building block for a lot of memory simulations is mem hierarchy, which provides caches, simple memory implementations, coherency modeling, and a variety of other tools. We talk a bit about that. We also have VaultSim-C, which is a model of a kind of generic stacked memory, similar to an HMC or HBM, but which can be kind of parameterized to look like a number of different things. Cassini, which is a library of cache prefetchers, which can be extended and added to do kind of simple types of streaming prefetchers. On the network side, we have a number of ways of driving our network. So there's the Ember library, which does pattern-based communication. So similar to Miranda for memory accesses, Ember can create patterns of network accesses. Using state machine-like models. Firefly is another network driver which encapsulates different communication protocols, so things like for a variety of MPI-like libraries. Hermes is an MPI-like driver interface which then connects, kind of acts as an intermediary between Ember and Firefly, allowing us to look at things like different collective models and kind of MPI matching and things of that sort. And then there's also Zodiac, which is a trace-based network driver. So we can take a trace of an existing application, feed that in. The main network model, which we'll be talking about, is Merlin, which is a network simulator. Merlin can simulate a variety of different topologies and a wide variety of different policies within that. Merlin and Miranda will be giving deep dives on tomorrow morning, but I'll very briefly have a couple of slides on those today, and then also just kind of briefly giving an overview of some of these other components. A couple of other components to know about. There's also Scheduler, which looks at job scheduling and resource allocation for a large system. And there's also the simple elements library of elements, which for someone getting started with SST are very useful. They don't model anything interesting by themselves, but they are good programming examples of how an element is constructed, how to use the statistics library, how to use clocks, links, and things of that sort. So the main goal of this next session is to sort of give a very high-end overview of a lot of these. Probably not enough that you can kind of hit the ground running, but enough so that you kind of know where to look for more details and kind of know what's already in SST. And hopefully you can inform us of any gaps, or when you start building your own simulations, kind of know which components you already have to begin building on and begin composing your own simulation framework. So a little bit more on some of the external components. We have a preliminary form of integration with Gem5. For those of you who are aware of Gem5, it's a combination of the GEMS memory model simulator from Wisconsin and the M5 simulator from University of Michigan. It provides a variety of simulators from cycle accurate to cycle approximate in and out of order processor models using execution-based simulation. It's heavily developed and heavily used at both ARM and AMD, and we're currently working with ARM on updating the integration of Gem5 with SST. So that's in progress, and we're kind of still working that into the regression test, but is available. There's also Maxim from Georgia Tech. This is a model of primarily we use it for GPU simulation, but it can also be used for other kind of highly parallel processor simulations. Some of the memory models we have, a lot of which are come from the University of Maryland. DRAM Sim 2 is a very validated DRAM model. Includes memory controllers and then a variety of DRAM models, primarily looking at DDR2 and 3 based systems, though it can be sort of tweaked to do DDR4 as well. NVDIMSIM models different non-volatile memory parameters. Hybrid Sim is a combination of DRAM Sim and NVDIMSIM, which also you can use to explore different policies and parameters for using DRAM as a cache to a slower non-volatile memory. And then the HBM simulator, which we'll be hearing more about this afternoon. So to kind of begin the World tour, we'll start with the Ariel. Ariel is a pin-based processor simulator. So if you're familiar with Intel's pin tool, it uses dynamic binary instrumentation, kind of similar to Valgrind or others, to modify an existing application in order to do different tracing capabilities or analysis capabilities. So in the case of Ariel, we use it to create a very lightweight processor core model. Intel's pin tool has decoders for a number of different x86 extensions, which we support, and also can support fixed thread count parallelism. So, for example, OpenMP or Q-threads, or sometimes, depending how the program is structured, P-threads. If you know how many threads you're going to be using at the beginning of time, you can create that many Ariel cores within SST and take traces from pin cores. So what it does is the application runs externally, pin attaches to it, instruments the binary, and then will pass information to a virtual core within SST. And it implements SST's memory interface in order to connect to the rest of the memory models, which we'll be hearing more about later. So the benefit of Ariel is that it tends to be much faster, roughly order of magnitude faster than a cycle-accurate processor model like Gem5. and it tends to give a reasonable approximation for studies, particularly if you're looking at memory applications which are bounded on the memory system, which tends to be how many of our scientific application work. We've used it for a lot of validation studies and found it to be reasonably accurate. And additionally, it gives a reasonable model of thread interaction, since you are actually executing code and the threads are synchronizing in different ways. The cons are that it is slower than a trace-based simulator or a pattern-based processor model, the kind of state machine models, which we'll be talking about later. And also it doesn't give cycle reproducible results, because you actually are executing the program in PIN. It's sort of left to the devices of the actual operating system's thread scheduling and synchronization mechanisms, so you're not guaranteed to get the same cycle reproducible results each time. Your program should complete correctly every time, but there are, of course, many different paths to correctness in a threaded application. So that is, you do have an element of non-determinism. Yeah.
Does it estimate how many cycles it thinks it'll take, or does it just say it took one cycle to do whatever you have?
So we're capturing the memory instructions from the application. So those are fed through the whole timing model. So we will get that. I think there is a mechanism where it can kind of take some guess for the non-memory instructions, but I don't think we're currently have that validated. So so in general, you will get timing information, but it's really just focusing on the memory aspect of the timing simulation. So yeah, it neglects some things. It's non-deterministic, and currently PIN only works with x86, so that's another limitation. And additionally, PIN itself, only works on Intel systems and things of that sort. So there are positives and negatives to it. In general, we found it to be a very useful processor model for looking at memory-bound applications. For us, a lot of our applications tend to be very memory-bound, so it works pretty well. A little bit more on the architecture behind Aerial. As I said, you take the user binary, which is actually run with Intel's PIN tool, which then does instrumentation. We've modified we've created a PIN tool which primarily focuses on capturing memory instructions, loads and stores, and all the myriad different formats that x86 wants to load and store things. These loads and stores will be passed into SST, into the Aerial component, where there will be a number of virtual Aerial cores. Each of these cores then connects to a memory interface, which usually connects to mem hierarchy, allowing us to simulate different caching strategies, different levels of cache, and all the way out to the network on chip, and beyond that to whatever main memory backing store you have, or multi-level memory. Additionally, we've instrumented the PIN tool in different ways to give some additional information. For example, we can kind of trace different mallocs. We have a facility to add different mallocs, which I'll talk about later, for doing experiments with multi-level memories. So you can say, allocate this to your fast memory, your slow memory. We can capture stack traces at different points in order to try to look at some different performance aspects. And primarily looked at different ways of remapping memory so that we can adapt it to different memory mapping schemes on the back end. Some more details on that. Aerial, as I said, creates a number of virtual cores inside. Currently, we're mainly just looking at the memory operations. The Aerial cores are clocked, and we can kind of set both the maximum number of memory requests they can issue per cycle, so you can sort of look at processors of different width, as well as the maximum number of instructions outstanding. So, and of course you can also change the clock period, which gives you some ability to limit performance. So doing that, there are some fairly coarse-grained, high-level knobs, but it does seem to give a reasonable amount of ability to customize your processor so that we can kind of use it for validation studies for different systems. Also, there is some back pressure from SST to the binary so that it doesn't completely run ahead of itself. Additionally, there's a mapping inside of the aerial core to kind of remap the virtual instructions from the application in different ways to SST. We can use this both to look at different effects of mapping memory to different memory controllers in SST, and also we're using it now to look at different multi-level memory allocation schemes. Inside of SST, Aerial connects to the memory interface, which generates mem events, a type of event which is passed between links to a number of different cache models. We also track basic statistics such as number of request counting, number of split cache line loads, things of that sort, total number of instructions executed, and basic information of that sort. So that's the aerial processor model. Again, gives some pros and cons. Much faster than cycle accurate models, but you do kind of accept some non-determinism in that case. Another processor model is, I'm sorry, were there any questions on aerial? Okay. So moving on, another processor model which we've been using is Prospero. This is a trace-based processor model, again, tracing memory instructions. So in this case, we have some tracing tools which read memory operations from a file and then pass them to our simulated memory system. So unlike Aerial, which is actually running a dynamically instrumented binary and taking a trace from that, Prospero is actually just reading from a file. Currently, the individual traces are sort of a single core trace, but you can use multiple trace files in order to emulate threaded or MPI style applications. And we have support for arbitrary length reads to account for different vector widths. And does a simple first touch kind of virtual to physical mapping in order to kind of construct its page table. We also have a Prospero trace tool, which I believe is normally based on the Intel pin tools as well, but also you can generate your own or translate your own traces to Prospero's tracing format because it is fairly simple to use. So the trade-off with Prospero is that for reasonable size files, it tends to be faster than Aerial and much faster than something like Gem 5, provided that you can find a trace of reasonable size and it will fit on your computer. It's again good for heavily memory-bound applications because we are just looking at the memory instruction trace, not the whole instruction trace, and tends to give reasonable approximation of memory system performance. The cons, of course, are kind of the cons of any trace-based simulation model. The traces can be very large, so it really requires a good I/O system to utilize it effectively. Also, traces tend to be less flexible than actual execution, and because we're only kind of capturing a single execution stream, it sort of takes some extrapolation to see what the impacts of threading would really look like. Give much more detail on Miranda tomorrow, but Miranda is a pattern-based or kind of state machine-based processor model. So this is an extremely lightweight processor model which generates a specific address pattern. Currently, we have support for a number of different address patterns, just kind of simple strided address patterns, both forward and backward, random access GUPS-like patterns, stream patterns mimicking the streams benchmark for both in-order and out-of-order CPUs, some kind of simple stencil patterns, sparse matrix patterns, and just kind of array patterns. The way, again, Miranda works is essentially you define something which looks very much like a simple state machine, which can be parameterized to emulate one of these patterns or other patterns you might come up with. The pros are that it's very lightweight, there's no binary to instrument, and there's no trace to gather, so it can be relatively fast. It's very good for applications whose address patterns are either very predictable, something like a stencil pattern, or ones who are very random, like GUPS. But it's not great for things which are doing, say, pointer chasing in a kind of complicated but patterned way. The con is that you need to create a generator for the memory pattern of interest, which kind of requires a good understanding of the pattern. So actually, defining the pattern is not too difficult. We'll be going into more detail on that tomorrow, but it does kind of understand that you know what the application is really doing in order to be able to capture it. So those are some of our 3 different processor models. Arial, which uses pin tool to dynamically instrument things. Prospero, which uses a trace-based format, and Miranda, which uses kind of a state machine like format to generate patterns. They all kind of give different pros and cons and give kind of a number of different options in terms of flexibility, performance, and accuracy. Any questions on those kind of processor models? All right. So next we'll talk about mem hierarchy. Mem hierarchy is another collection of components which really become a meeting place for a number of other components within SST. As you might guess from its name, mem hierarchy, of course, is modeling a memory hierarchy, primarily the caches, directory controllers, and memory controllers for a single node. On one side, these will often connect with processor models like Gem5, Arial, Prospero, or Miranda, and on the other side, they can connect to main memory models like DRAM Sim2, Vault Sim, or the high bandwidth memory model. And sort of in between those, we can use Merlin, our network model, to do things like simulate a network on chip. So this could be something like a simple mesh network to look at a tiled architecture, or like ring networks to look at like Haswell or Broadwell type modern processors, examining the kind of impacts of network on a chip there. At a high level, mem hierarchy does caches as well as modeling all the cache coherency. So mem hierarchy does the memory system. It's a cycle accurate cache and memory simulation. It has support for both inter and intra socket coherence, and connects to multiple main memory models. It aims to be very highly configurable, so you can do any number of caches from just a simple L1 all the way up to, if you want, an L10 or L20 levels of cache hierarchy for, I don't know, just to torment someone, I guess. You can also connect these in arbitrary topologies, so caches can be either private or shared, and you can connect multiple memories on the back end, so you can have multiple backing stores, including multi-level backing stores where you have heterogeneous memory acting as your backing store. There are configurations for both single and multi-socket, and we've used this to model a number of modern memory hierarchies and done validation studies on a number of these. So a lot of things like Intel i7 family of architectures, Xeon Phis, a variety of ARM architectures from the A7 and 8s all the way up to the A50X series, and also done some modeling the Spark T6 cores, or architecture. Some of the individual components which make up the mem hierarchy library, there are of course cache components, are kind of the core of this, and these include the different coherency protocols, MSI, MESI. Do you have any others, or are those the...
There's an incoherent, which I think is used for GPU. I don't use it, but other people do.
So yeah, cache and coherency optional. There are buses, shared buses for coherency, or they can connect point to point. There's also directory controllers, including ones which model inter-socket coherence, or ones which are not aware of that. There's memory controllers of different sorts, which backs up the simulated memory and also interfaces with a variety of memory backends, things like, again, DRAM Sim2, different 3D memory models, or non-volatile memory models. As the next point says. Just for testing purposes, there are also some very, very simple CPU models, trivial CPU and stream CPU, which are just simple address generators, which we use internally for testing.
Question.
Oh, yes.
So for interacting with DRAM Sim and RAM Sim, or I don't remember, hybrid Sim, does mem hierarchy use a unified interface?
How do you mean by unified?
Like the same interface for calling different external libraries.
Yeah, yeah. In the case of like DRAM Sim and NVDIMM Sim, they tend to use the same interface. All of the cache components, they don't really know what the backing store looks like. It's actually handled with modules at the memory controller part. So yeah, they can load in dynamically different modules to interface with, say, DRAM sim versus NVDIMM sim, something of that sort. So yeah, it's pretty unified.
It's basically a translation shim between the mem hierarchy components and whatever other simulator you're looking to use.
So a bit on the caches. So the caches are actually storing data. They'd be very easy to integrate with, say, a true execution-based simulator. You have the normal sets of parameters which you can imagine for cache. You can change site associativity. You have configurable replacement policies, LRU, least frequently used, random or pseudo-random, MRU, and MRU. It uses MSHRs to buffer outstanding requests. So those are limited, and it communicate either using a bus where it models bus contention via a direct link, so your L1 say directly connected to an L2, or through a network. So your one level of cache communicates through a network on chip to the next level. It does this through some of the standardized interfaces in SST, specifically Simple Network via the memNIC module, which is a module which can be loaded into your cache in order to connect to, say, the Merlin networks. So you can model a single shared cache or multiple cache slices. So your cache can be kind of broken up and sliced. This is common in some Intel architectures. The cache models have support for atomics and non-cacheable requests. There's also the Cassini element library, which is closely related. This is a library of cache prefetchers. So you can do just mainly simple block look ahead and streaming prefetchers, which have their own kind of sets of configuration parameters to detect strides and things of that sort. Internally, a cache looks kind of like this. You have the actual cache controller, which routes incoming events to different handlers and subcomponents within the cache. It also manages retry of buffered events and will manage all the different cache allocations and evictions. The cache array stores the actual cache lines, both the actual data and metadata, particularly coherent state, and performs replacements based on the replacement policy manager. The MSHRs are buffers which kind of store the stalled and blocked events for the cache and are managed by the cache controller. And then you have a separate coherency controller, which of course manages the coherency state, receives events and control messages from the cache controller, and is in charge of sending outgoing coherency related events, things like forwarding requests, responding to coherency requests, and deciding when events need to stall. What this means for the person who is just using memory models or cache models is that there's a lot of detail which you don't need to reinvent. And what it means for the person who is developing new cache models, or new coherency protocols or policies, is that internally our caches are broken down in a very modular way, so that if you do want to add new coherency protocols or explore new replacement policies or something of that sort, it's done in a fairly bounded fashion and won't require completely reinventing or getting your fingers into all parts of the cache. Again, it's even at a subcomponent granularity, it's designed to be very modular and easy to expand. This is come in handy for us in that we've added an increasing number of complexity to our caches, from very simple caches with only one hardwired coherency protocol. Now we have a variety of coherency protocols, an ever-increasing set of replacement policies. We can do things like sliced caches and distributed caches as well. So it provides a very flexible and modular set of building blocks to develop and explore cache hierarchies. Another aspect of mem hierarchy, of course, is the main memory, which we talked about. Main memory does have a true backing store for simulated data. So again, this makes it easy to interface with an actual execution-based processor model. The memory controller can communicate either over a network or via a direct link. So you can either have your last level of cache talk directly to your memory controller, or you can have an arbitrary topology network in between the two, so you can look at, say, a ring or mesh, and can have a lot of flexibility in how you wire those different components together. And also, because of that kind of arbitrary flexibility, you have the ability to interface multiple memory backends with your cache. So what this means is you can choose from our handsome list of available backends, simple memory, which just gives a basic read-write with associated latencies and sort of a very rough bandwidth control. Or you have the DRAM Sim2 models, which give very detailed timing models for the state machines for different DDR 2 and 3 memories, or to some extent 4, NVDIMM Sim and Hybrid Sim, as we mentioned, or Vault Sim, which is kind of a whole set of simulation components into itself to look at different configurations for stacked memories. Another aspect of the memory, because you have this kind of arbitrary topology, is that it's possible to explore having multiple types of memory backends. So, for example, a DDR plus non-volatile memory, you can do that by simply plugging in, instantiating a DRAM Sim2 component and instantiating a NVDIMM Sim component, assigning them different bases of the address space and plugging them into that network on chip allows you to simulate what the effects of multiple backends are, and then using different front ends like the aerial front end, you can sort of create different mallocs which target those, or just assign different chunks of the address space to look at different aspects of your memory system. Or you could create a kind of specialized memory backend which simulates automatically moving data between those different types of memory on your backend. We'll talk a little bit more about that later. So in general, mem hierarchy, it is sort of the meeting place of the main memory and the processor models. It provides you the ability to create an arbitrary depth of cache hierarchy connected with different topologies and network on chip, and the ability to choose from either one, multiple, or heterogeneous memory backends. This gives you a lot of flexibility for how you connect your processor models and your memory models, and a lot of flexibility for your cache hierarchy, including all the flexibility you would imagine for changing things like coherency, associativity, cache sizes, of course, all the bells and whistles which you generally would want. And if there's some which we haven't thought of, the internal structure is fairly modular, so you can add things like prefetchers, new replacement policies, and so forth. Any questions on mem hierarchy? So I'll speak very briefly on Merlin, our network simulator. Again, tomorrow morning there'll be a real deep dive in an API program, so there's sort of a serial flow of control within the motif, with many motifs then acting together in concert to simulate whole parallel behavior. An example of some of the motifs which we've implemented are different dimensional halo exchanges, 1, 2, and 3 dimensional. We also have motifs which encapsulate some popular MPI collections like reductions, all gathers, all reduces and gathers and barriers, and some communication sweeping behaviors like in Sweep 3D or in LU decomposition. So these motifs, as I said, are state machines which are interpreted and managed by the Ember engine, which manages those motifs. The Ember engine will create an event queue into which the motif kind of adds events whenever needed. So essentially the Ember engine is pulling communication events from the actual motif. This engine executes the queued events in order, converting them to message semantic calls as needed. So it can take a kind of high-level collective call and translate it down a little bit. And then just pulling these until the kind of either motif signals that the communication is done or the simulation itself comes to an end. And these events are, again, at a fairly high level, things like send, receive, or collective. And we also have the ability to add kind of pauses in this computation to simulate compute at different levels of granularity. So there's sort of an event which just says, compute for a period, and will cause the Ember engine to wait before issuing further communication events, so that you can look at the effect of different different overlap of communication and computation. This is an area where I don't think it's in the current lease, but they're looking to extend to have that compute for a period event, which right now is just a pause, be more parameterizable in different ways, so you can connect it to other SST components to get a more bounded feel for timing.
Yeah, so that's to say, currently, if you had some MPI operation that has a progressive computation going through it, like a reduce with an add that does something on the way through, that would have to be through a compute for a period. Now, you can't actually connect that to components at present.
Correct. Yeah, currently the compute for a period is just sort of a pause. If you had like an MPI, are you talking about like a reduction, which is doing an add?
Sure, something like that.
So in that case, I don't think it's simulating that additional add as a compute because it's fairly small. This is more for if you were like doing a like a ghost cell exchange, you would have a communication to send those ghost cells, and then a compute for a period as you simulate the computation.
So that's like explicit computes that are part of the application.
Right.
Okay.
Yeah. And we are looking at plugging that into being able to connect to other SSD components. So you could look at, say, as you change your memory system, how would that compute for a period evolve? So Ember kind of provides this set of motifs as well as the ability to extend and add different motifs and look at these high-level communication patterns. Underneath Ember is kind of the Firefly and Hades components, which are useful for simulating large networks and which provide an additional set of drivers. So Ember provides the kind of high-level communication pattern. Firefly and Hades provide the translation of that high-level communication into actual events and actual communications. So if you imagine Ember is sort of the driver, and then Firefly and Hades provide the kind of communication library in the NIC, and then something like Merlin would provide the router and the actual simulation of the network. So nodes are connected together via these different routers, Merlin, to form a network, and sort of at each endpoint you would have this stack which performs the messaging and communication. So in the case of Hades, it's a module which takes those high-level events that Ember creates, things like your all reduce, and will actually reduce that into a series of point-to-point computation or communications. Yeah.
Where, if at all, does adaptive routing fit in there?
So adaptive routing comes in the Merlin router, and I think we'll probably talk more about that tomorrow. So just like their current systems, the MPI library doesn't really do the adaptive routing. It's actually more in the NIC and router layer. That's kind of the way we simulate it as well. I believe Ember and Firefly does have some information, so you could at least get kind of queue depths and things of that sort. So if you wanted to, say, create a motif model which was trying to maybe adapt its communication patterns, you could do that, but I don't think we have any motifs which do that currently. Ember is this kind of state machine which is creating sends, receives, and collective communication requests. Hades will take those sends, receives, and collectives and actually turn those into a series of optimized point-to-point collectives. So, for example, if it gets an all reduce, it will turn that into a tree sort of structure to do the reduction. And then those kind of point-to-point communications are then passed to the Firefly component, which is actually simulating a NIC. So there it simulates packetization, will deal with the flow control as it communicates with the actual router, and also deal with things like message ordering semantics and things of that sort. One of the benefits for simulating, for example, MPI applications on large machines is Firefly and Hades will actually perform the MPI matching semantics. So in MPI systems, when a message comes in, there's an ordered list of which it has to be compared against. We can parameterize how long those matching operations take, so we can actually look at how much that will limit our ability to receive messages, which on large systems will actually often end up being a fairly important limiting factor in overall performance of MPI applications. And those things are parameterizable, so we could look at, for instance, what if we had specialized hardware to optimize that, or what if we tried to do some things at the MPI library level to improve that matching or ordering. So Ember, Firefly, Hades, and Firefly are all create a little network stack which plugs into our Merlin series of components in order to provide a scalable simulation framework for looking at high performance networks. We can scale this up to large hundreds of thousands of nodes. We can also take just the Merlin component of that, break it off, and use that for looking at much smaller networks, networks on chip, which say connect to memory hierarchy. This sort of composability of having a series of core components and interfaces which we can plug different things into, drive in different ways, from either treating it as a processor model or a high-level network, is kind of one of the core abilities of SST to provide these different components which you can, in a modular fashion, build up a variety of different simulation levels.
And it should be noted that the Firefly NIC implements a simple network interface. So we've had people that we've worked with, and they started using Merlin, and then they wrote their own router models and could still connect into the same infrastructure through this. All they did is implement simple network for their router models, plug that subcomponent in instead, and everything still works. So it's fairly modular as far as mixing and matching, as long as you use those core interfaces.
And the simple network interface is basically just an event interface which has...
Yeah, we'll look at simple network a little more when we look at Merlin tomorrow. But essentially, it defines a request object, and you fill in that request object. You can then put an event into that request object, and it essentially just delivers the event to the other side using the header information in the request object. That's how the simple network works.
So let's see, one other kind of interesting set of components is the scheduler library. This models a large system, kind of system-wide job scheduling and resource allocation. So this would be if you wanted to look at, well, I've got 1,000 nodes and 500 jobs to execute. How would those actually be scheduled across? It's comprised of three components: a scheduler component, which actually does that scheduling; different node components, which run the scheduled jobs in a very, very, very simple high-level way, and also some fault injection components where we can look at, if we inject faults, how do those propagate through the system. Again, this modeling is at a very high-level matter. It's not actually looking at anything at even the circuit level. It's just kind of looking at it, viewing the system the way that a very high-level job scheduler might look at things.
So with the fault injection, is it constant or is it variable? Can you vary it?
You can vary it. And I think you can, I believe it has, you can either do, it has a few different probability distributions which you can choose from, and you can kind of vary the, parameter, different parameters into those. So you can look at fault injections under different schemes.
Can you create your own?
Yes, yeah, I believe so. Currently the scheduler, originally was developed to just sort of work as a standalone set of components. We're currently looking at plugging those into the kind of Ember, Hades, Firefly, Merlin stack so that you can analyze the effect not only of different scheduling algorithms, but also how those scheduling algorithms would influence network performance. So if you had, say, crosstalk between two different applications scheduled onto the same machine, how does that actually impact performance? And then how should the scheduler be modified to take advantage of that or to minimize those effects? So yeah, scheduler is another kind of set of components which is being developed and is also kind of further integrating into the wider set of components through these standard interfaces. There are a few other libraries which we'll get into, particularly some of the example libraries, which are very useful starting points for understanding how SST components are written. More detail can be found on our website, ssdsimulator.org. So next I'm going to briefly talk about some of the different use cases, kind of examples of how we've used SST to explore different things, and how SST can be extended. Before I jump to that, are there any other questions on the any of the libraries or components we talked about? All right. So